Now that we have discussed principal component analysis in some detail, and I have explained figures 4.4 and 4.6 in your text, let's move on to figure 4.7 and also table 4.8, and I'll explain those in this video. Notice in figure 4.7 that if lines perpendicular to the first principal component are drawn through each data point, right here, that the metric location of each intersection corresponds to the component scores that we calculated previously in video 4.13. Now, a quick explanation. These lines drawn perpendicular to the first principal component are called isoquants. Now, isoquants are lines marking equal quantitative value. Each of the 6 isoquants here in this figure marks the locations that have equal value projections onto component 1. Similar isoquants could be constructed for component 2 or any of the variables. Since these data have a rank of 2, all 5 sets of isoquants, which are 3 variables and 2 components, would have perfect metric properties. Now, if we go to, let me go to Excel here from the calculations we did on video 4.13. We look here at what we calculated, this little matrix that I've highlighted down here, which are the scores of each of the 6 persons on the 2 principal components, these are also called factor scores or latent scores. Now, if we look at that, we can see that the metric location of each intersection of the isoquants in figure 4.7 corresponds to these scores. And I'll go to that here. So for E, we have 25.92, for A, 23.99. We have got 19.38 for B, 18.47 D, 12.96 F, and for C, 10.12. Now, the information from principal component analysis can be collected into a summary table, as was demonstrated for factor analysis. However, the table will be more informative if the coefficient matrix K is first rescaled by pre-multiplying it by lambda raised to the 1/2 power, which is the square root of the diagonal matrix of eigenvalues. And I'm going to do that in Excel here. So we're going to post-multiply K, which is the matrix of eigenvectors that we got, by lambda to the 1/2, the square root of the diagonal matrix of eigenvalues. So this normalizes the eigenvectors to their eigenvalues, as it was done in creating factor loadings in factor analysis. It should be noted, however, that whereas this process applied to factor analysis, which involved a correlation matrix, creates factor loadings that can be interpreted as correlation coefficients between the manifest variables and the factors. The same is not true of this. The same is not true of these scaled principal component analysis coefficient. So rather than labeling them as F, which were the factor loadings, we'll designate them as K sub SC, which will stand for scaled coefficients. So I will calculate that here. I'm just going to copy and paste. And this matrix will have diagonals that are the square root of the eigenvalues. And when we multiply these matrices together, this is what we get. And this is what you see in the table 4.8, the PCA summary table for simplest case data with a rank of 2 that you see here. So these are the scaled coefficients that we just calculated. So using scaled coefficients for the summary table, the sum of the squared coefficient, so we just squared these and put these in the squared coefficient portion. The sum of these is going to equal, going down, the sum of these is going to equal the eigenvalues, as they should be. Now, to obtain the percents of eigenvalues, the eigenvalues are divided by the trace of the S matrix, the covariance matrix, or the sum of all the variance units, which is equal to 42.4. It is important to note also from this summary table that the row tables of the squared coefficients, so here, are the variances of the three manifest variables: math test, verbal test, reasoning test. The two column totals, so we have 37.379 and 5.021, as I just explained, are the eigenvalues, the variances of the latent variables or the components. Now, the reason the row and column totals are equivalent to the variances of the three variables and the eigenvalues of the two components respectively is because we created data that fit the two-component PCA model perfectly, or in other words, we had data with a rank of 2. And I mentioned this in the last couple of videos. Now, where empirically derived data, where the rank is greater than 2, these statistics for a two-component PCA model would indicate the number of variance units accounted for by the model rather than the total amount of variance in the data. We only have a perfect number, like I said, because it's rank of 2 and the data fits perfectly. The sum of sums of all the squared coefficients, so 4 plus 16 plus 22.4, does in fact equal 42.4, and is the total amount of variance in the data set. And therefore, the trace of both the covariance matrix, S, and also the matrix of eigenvalues, lambda. So, just to recap, this video was an explanation of figure 4.7, which used isoquant projections, these lines, of the 6 multivariate data points on the first principal component. And I also explained table 4.8, the PCA summary table for simplest case data with a rank of 2, and we noticed that all of the variance is accounted for.